Hi, I'm Amanda Jones, and I'm going to talk you through the binary system. Now, our system, our numeration system, is base 10, which means that in each place value, each digit in the numeral is multiplied by a power of 10. Now, binary has that prefix of bi, so it is base 2. And so that means that each digit in the place value is multiplied by a power of 2. The other thing about moving to other bases other than our base 10 system is that we're only working with that many digits. So if you're in a base 10, you have 10 digits, okay? 0 through 9, there's 10 digits there. And so when we back down to base 2, we only have 2 digits to work with. So when we're in binary, we only use the digits 0 and 1. They're the only ones that we can use, and we put them in a string to represent a numeral, and each 1 or 0 is multiplied by a power of 2. So let's talk about the powers of 2 real quick. It's always helpful to start there when we're building with our with new bases and new numeration systems. So powers of 2, we'd start with our ones place, which is 2 to the 0. Always easy to forget that, but it's so necessary that we have to have a ones place. So we always start with a base to the 0 power as our first place value in our numeral, okay? 2 to the first power, of course, is 2, so we'll have our ones place, our twos place. 2 squared is 4, our fours place, and so on. Two to the fourth is 16. 2 to the fifth is 32. We'll stop there for now, but you know the next one is 64 and so on. And so having this and just remembering this as we talk through binary is helpful. Note that these are not doubling, or they're not multiplying by 2, they are doubling. So they are doubling if you're counting by powers of 2, which can kind of be tempting to just think 1, 2, 4, 8. Just make sure you're not going 2, 4, 6. So sometimes that's tempting. They are powers of 2, not multiples of 2. So there is a difference there. Just like with the base 10, we're going 10, 100, 1,000, and so on, and not 10, 20, 30 with our place values. So think back to that base 10 system. Other bases operate just like it, just with a different base to the exponent. Same exponents, same framework, just a different base in the multiplication when you're thinking about the expanded form with exponents, okay? So let's just count a little bit in binary. So we'll start with representing 0 in binary, and that's just going to be 0. Real easy there. 1 in binary is 1. To kind of distinguish between base 10 and binary, usually base 10 is left alone because that's what we're used to, and then the new base is, if it's in a different base other than 10, then the base is written kind of as a subscript to the numeral. We tend to drop it in base 2 because we see these strings of 0 and 1, and we assume binary along with context. So you won't see me writing the 2s with the binary. I just wanted to go ahead and present that and make that distinction, at least now, right now, while we're counting, okay? So now I want to represent the quantity 2 in binary. And I don't have a digit for 2, I just have 0s and 1s. So now I have to move into a place value to represent 2. Well, remember that our second place value in binary is a 2's place. 1, 2, 4, 8, 16, 32, and so on. And so that is when we move into our next place value, putting a 1 in the 2's place, and then our 0 as a placeholder in our 1's place. So this, if we were to write it in expanded form with exponents, would be 1 times 2 to the first power, because we have a 1 in the 2's place, plus 0, because we have a 0 in the next place, times 2 to the 0 power. So there you can see that if we were to do this multiplication in addition, it would be 2. It'll get us back to the quantity of 2. So let's keep going. We'll go to 3. Okay, so think about what 3 might be. 3 is going to have a 1 in the 2's place, and then we need another 1 in the 1's place. So it'll be 1, 1. Don't say this is 11 because it's in base 2. Say it as 1, 1. That's how you'll hear us say it when we're in a different base. We just say the string of digits. Okay, so you can do this in expanded form. It's 1 times 2 to the first power plus 1 times 2 to the 0 power. So 2 plus 1 equals 3. At this point, this is kind of like being in 99 in our base 10 system. We're at the highest digit and we've kind of maxed out each place value with a 9. In this case, we've maxed out each place value with a 1, which is our highest digit in binary. And so at that point, that's when we add our next place value. Also, 4 is the next one, is a power of 2. We know that it's 2 squared, so it makes sense that it would move up and have a 1 in the 4's place, no 2's, no 1's. So we've added a new place value. So I'm not going to write it out, but 1 times 2 squared plus 0 times 2 to the first power plus 0 times 2 to the 0 power. Okay, so 5, we would have a 4, no 2's, and a 1. So 4, no 2's, and a 1. So 4 plus 1 is 5. Keep going just a little longer. 6, that's when we would need a 4. We can't go any further than a 4. An 8 would be the next power of 2, and it's too big to go into 6. So that's how we know that we still are at only 3 digits. We also haven't maxed out all of our place values here. Okay, so 6 is a 4 and a 2 and no 1's. And then 7 is where we max out place values, a 4, a 2, and a 1. And then 8, which is another power of 2, is going to go to the next place value, 1, 8, no 4's, no 2's, no 1's. And then you'll kind of see that pattern continue. It's fun to write these out and see that pattern kind of develop as you move on and add new place values and when that new place value is added. But let's move on at this point and just do some translation between binary and base 10. So start the easier way, in my opinion, is to go from binary to base 10, and then we'll reverse it and take a base 10 number and write it in binary. All right. So what if we had 1, 0, 1, 1? So 4 digits in the numeral. And sometimes I like to go ahead and think about all my powers of 2 again and even write it out in these little blanks. So I can like put out, I'm going to go ahead and put 5 of these out. Okay, and do 2 to the 0, 2 to the 1, and like write in my place value. This is kind of writing like 1s, 10s, 100s in those place values of our numerals. So just to make sure that I'm thinking powers of 2, I'm going to write this first, and then I'm going to write what they're equal to help us out a little bit. So 2 to the 0 is 1, 2 to the first power is 2, 2 squared is 4, 2 to the third is 8, and 2 to the fourth is 16. You can, of course, keep on going depending on how many digits you're needing to translate. Okay, and so I know that if there's a 1 in this place value, then I'm going to have a 1. If there's a 1 in this place value, I'm going to have an 8, and so on. So you can see that I do that. I have a 1 in that 4th place value right here. So that's right there. It's not a 1. It's a 1 times 2 to the third. So it's actually an 8 because it's in that place value. So I'm going to go ahead and write it in expanded form so we can really see it. 1 times 2 to the third power plus 0 times 2 squared. Some people don't write this. That's okay. You're just figuring this out. This is your work, okay? And so write it or don't write it depending on how you feel about that. I like to write it just to see that it's there and that I haven't forgotten it because I like to see all my powers. Okay, so 1 times 2 to the third power, 0 times 2 squared, 1 times 2 to the first, and 1 times 2 to 0, 1, 0, 1, 1. So these are my digits in my numeral, and then their corresponding place value that they're getting multiplied by. So we have 1 times 2 to the third, which is 8, plus 0. 1 times 2 to the first power is 2. And 1 times 2 to the 0 is 1. So 8 plus 2 plus 1, this numeral represents the quantity of 11. So binary 1011 represents a quantity of 11. Okay? And then let's do another binary number. Get a little bit bigger. This one is really just the same though, because it still only has, the last one had 3 ones, this one has 2 ones, so it's almost easier to just think about, okay, what place value is this one in and what place value is this one in, and add those two quantities together. So that's one way to make it a little quicker. Writing it out full expanded form, we are in the 1, 2, 3, 4, 5th place, which is 2 to the 4th. Careful with that, because it starts at 0. So we're in the 2 to the 4th place here. So 1 times 2 to the 4th, plus 0 times 2 to the 3rd, 0 times 2 squared, 1 times 2 to the first power. So I didn't write all the zeros this time. Okay, so 1 times 2 to the 4th is 16. 1 times 2 is 2. This binary numeral represents the quantity of 18. Okay, let's go in reverse now. I think that the reverse, like I said, is a little bit more challenging. I'm going to leave this up. So what if we wanted to represent the quantity 12 in binary? Okay, so once again, thinking about our powers of 2, what I like to do is think about the biggest power of 2 that will fit into 12. So 8 will fit into 12, but 16 will not. So I know that I'm going to have 4 digits in my numeral because I cannot get up to this 16. It doesn't fit into 12. So I'm already going ahead and thinking I need 4 digits. I am going to need an 8, okay? And 12 minus 8 is 4, so I still need 4 more to represent what this quantity is. So I have my 8. I need 4 more, so my next place value is a 4, so I'm going to go ahead and put a 1 in the 4th place. And then I do know that I need, now I'm at 12, but I still need those 2 0 placeholders to show that this is not just in this place, but it's all the way up into this 4th place value, which is 2 to the 3rd and 8. Okay? And then let's move to, let's represent 22. So quantity of 22 converting to binary. Okay? So the one after 2 to the 4th is 2 to the 5th, which is 32. I like to see that to just know that it's not going to fit into this. So I know I'm going to be starting with a 1 in the 16's place. And then I do that subtraction, like how much is left to represent. I know this is 1 times 2 to the 4th, so I've got 16. How much more do I need? 22 minus 16 is 8. Okay, so 8 more. All right, nice. That's my next place value. Okay, so 16. Excuse me, I did that math wrong. Let me back up. All right, so the next number that we're going to represent is 22. Okay, so I went ahead and put up that 2 to the 5th is 32. I want to see what is next so that I know that it does not fit into the number that I'm trying to represent here. So I went ahead and wrote 2 to the 5th is 32. And so too big to fit. And so I know that I'm going to start with a 16, and I'm going to have 1, 2, 3, 4, 5 digits in my numeral. So I'm going to write that 1, keeping in mind that it is in this place value. Okay, and so 16 is taken care of. What do I have left? You can do that subtraction. 22 minus 16 is 6, and so you know you have 6 more that you need to represent. You know that 8 does not fit because 16 plus 8 is too big. It's not 22, it's over 22, and so I don't have any 8s. Okay, now 16 plus 4 is 20. I do need a 4. And I have 2 more left, and so I know that I'm going to put a 2 in, and then I've got to have a placeholder in the 1. This is 22, placeholder in 1. Okay, one more. Let's do a larger number. Let's do 67. All right, so let me keep on moving here. I need another place value. 2 to the 6th is 64. And then, of course, we would go to 128, 2 to the 7th. That does not fit in there, so we're going to be starting right here in this place value with 64. So go ahead and put a 1 in that 64 spot, and I know I'm going to need this many digits, 1, 2, 3, 4, 5, 6, 7 digits in this numeral. But I've already got 64 taken care of. I only need 3 more to get to that 67. So no 32s. No 16s, too big. If I were to add 16 to 64, if I added 8 to 64, it would go over, so no 8s, no 4s. But we do need a 2. Now we're at 66. 64 plus 2 is 66, and then a 1. So sometimes big numbers really aren't too difficult because they don't require a whole lot of 1s and a whole lot of thought. So that is binary and how to represent things in base 2 and convert a base 10 into a base 2. Thank you.